Mamy... Czy ktoś mi zapowie? Tak, czy nie? The time is ticking. I have just 2 slides, so I will wait. Hi. Good afternoon. This is the last presentation on this track. I believe you all came here for John Sandel, but he will be next. So you can stay just 45 minutes about. Yeah, how to use crypto. You know crypto? What is the crypto? Well, it's a very hot topic. Blockchain? Something? No? So, what if the crypto is the new gold? But what should we choose? We have Ethereum, Bitcoin, Litecoin. Well, it's very hard. So, yeah, maybe let's do Bitcoin for beginners. Oh, wait! Yeah, we just got an alert from the President of the United States that crypto is for cryptography. Remember that. So if you ever hear crypto, it's not about cryptocurrency, it's about cryptography. My name is Marcin Krzyzanowski. I work at PSPDFKit and I built the PDF framework there. You can find me on Twitter. I have a blog, and I have a GitHub account with some projects. I have 2 projects that are related to cryptography. The CryptoSwift, that was the foundation for today's talk, and Objective PGP, that is the implementation of OpenPGP protocol. You may be familiar with this protocol. This is the protocol that you use to encrypt the emails. During this talk, I will base on my experience with the CryptoSwift project. And this is the project that implements crypto primitives in Swift. It might be a bit low level to some of you, but if we have some cryptographers here, do we? If you are a cryptographer, please raise your hand. Good. Okay, I can say anything. So yeah, so let's start. The talk is around the issues I got reported to the repository of the CryptoSwift, and yeah, they will explain the basics. You may think that a project like CryptoSwift, so the cryptography, is about the cryptography. So all the issues are about the cryptography. Well, it turns out that about the half of the issues is about cartridge, CocoaPods, Swift Packet Manager, Swift versions. If you deal with that, well, you will get, I get the questions, I don't know what I'm doing, but it's not working. And about the 10% is actually about the crypto and the bugs I had in the code base or the feature requests. I think that after this presentation, you'll feel more confident about encryption in your app on a low level. So yeah, let's start with something basic. This one was reported just a few days ago, but it's a good example of the most common issue I face in issues. So what do we have here? The description says, the string cannot be reproduced from the encrypted unsigned int 8 array. Right? So the unsigned int 8 is byte, which means it's 8 bits. Do you know if this is true for every architecture? Who thinks it isn't? You can raise your hand and say the value. Well, it isn't. On a PDP-10, nobody used that. Actually, byte is 7 bits. But today we can assume that byte is 8 bits. Okay, so the problem is I encrypted some message, and then when I try to print out the encrypted message, well, it crashes. It crashes here because this is Swift, and Swift never crashes. This is Swift, so he get nil and he unwrapped it. So yeah, at the end, he get a crash. But this is the problem, right? To say what's going on, I draw the diagram for you. Yeah, because I got the iPads and with this pencil, and I like to draw, so everything is drawn. Let's say we have a message lorem ipsum, right? It's a string, so this is something we want to encrypt. This message can be represented as sequence of bytes here. This is lorem ipsum. There's a bytes. And the bytes, each byte can be represented as bits, right? A series of bits. Each byte is 8 bits. That bits go to the encryption machine that do the magic and output some shuffled bits that we can again represent as a bytes. And yeah, and we want to print out the result. So who knows what's going on here? If you know, yeah, you get a reward. Why it fail? Why this encrypted the ciphertext?
Maybe the assumption that one letter is called by bytes?
Yeah. So I will not repeat because I want to say that. But you're right. You're right. Yes. So let's think, what is a string? A string is the sequence of the characters, right? What is character? A character is most likely 1 byte that represents some letter, right? If we have that letter, we can bytes represent as letter. What was the oldest encoding you may think of for the string? ASCII, right? So ASCII use half of the byte, 127 values that was encoded to the values were encoded to characters. And we had a text or something. And at the end, in C, at the end there is empty value 0. That means this is the beginning of the string, something, something, end of the string because there is 0. In Swift, that will be different. In Swift, there will be like a struct that has some message, some text with the length as a different value, and based on that, you can what? You can interpret the values as text, right? That means if we encrypt and we get some random values here, it not necessarily will form a correct string because there's no assumption that this will be string. Let's say it's C and the first byte is 0. That means this is the end of the message, right? And C will just say, okay, this is the string, 0 length string, and go away. So the problem was that the reporter, wanted to interpret the ciphertext as UTF-8. And this is basically false assumption. can it be the value? Can it be presented as a string? What do you think? Is it possible at all? What converted bytes to the? Yeah, basically. So we have to use encoding. This is the main confusion. The encryption is not encoding. That distinct mechanism. Encryption works on a bytes, on a very low level. Actually, encryption works on a bits. It's shuffled bits. But encoding is something that transforms data from one form to another form, but information is not changed. It's still the same information. It's just represented in a different way. You may be familiar with base 64 or just hex representation. Like here, it's not visible, but there's a bytes represented as a string. So that would be the solution to the issue. What is the encryption? Well, I already said that encryption is not encoding. So encryption would be shuffling the message using a given key to a form that looks random and can be reverted to an original form without losing any information. What is the safest known encryption technique today? There is one, and it's more than 100 years old. It's called one-time pad. One-time pad is an encryption technique that cannot be cracked, but the problem is that it requires the use of one-time pre-shared key the same size or longer than the message being sent. So we have to generate some random key that is at least as long as the message, and use some operation here that in the early days it was adding, but today we will use XORing probably, to get the output. You can imagine that sending a simple PDF document would require another document of the same size just for the key. So it's very unpractical. Due to that practical considerations is not very often used, but it was during the Second War, for example. What kind of encryption do we have? We have a symmetric key encryption. Symmetric key encryption is an encryption that we use the same key for encrypt and to decrypt message, basically. So this is the symmetry. And how it works? Well, basically it's XORing. You know what XOR is? It's a logical operation, exclusive OR. And it can be represented like this. Why XOR is the tool for encryption and for hashing as well. Because there's a 50% chance that for given value 0 or 1, you will get 0 or 1, right? There's a 50, so it's equal. There's no advantage. You cannot think of any advantage when you give you input. It's other with the AND, like this is 0, most likely get 0. With OR, most likely get 1, so it's not really good. Another type of encryption is asymmetric key encryption. This is the Diffie-Hellman RSA. It's a public-private key encryption, and it's based on the math based on the assumption that finding some particular number is hard enough for the computer. So it's that hard that we can assume that the computer will never find it without knowing both sides. Okay. Let's assume you want to encrypt something, and this is your first task on encryption. That was Jira issue. So you go to the Google, you go to, or Stack Overflow, whatever, and this, most likely, you will find the snippet like this one. Because, why? Because there's a common crypto. Common crypto on iOS is the system, I don't think it's a module now, but it's a library. So yeah, you will find this. There is 12 parameters you have to fill in. And there are a few that you might be not really familiar with, but you have to choose something. The one is algorithm. The other one is padding. The key, IV. I will talk about IV. And the other one is just a buffer. So that's fine. But this, you can make a mistake choosing any of it. Similar with the same common crypto, the similar method, you have even more. There is a block mode. You have to choose a block mode. What is the block mode, right? At some point, you may figure out even that you can skip this value IV. If you pass the nil here, or null, it will work. Just for the record, this is the version of the CryptoSwift library, but really, it may look prettier, but it asks you for the same parameters. The cipher, algorithm, the key, the block mode, the IV, and the padding. I will try to tell you how it works, what are the values, but start with the cipher. CIPHER is the encryption machine, the magic box we use to encrypt data, right? There are a lot of ciphers out there. There's one that is most popular, AES, Advanced Encryption Standard. It's everywhere. It's even in hardware, like not totally in the hardware, but the most crucial part can be executed by the processor. There's special instruction on the Intel and on ARM for sure. So it's fast as well. And it's mathematically proven that this is a safe cipher, but can be used wrong. It's safe in theory, but can be used wrong. What type of ciphers do we have? We have stream ciphers and block ciphers. Stream cipher works with basically with the stream data. You know what a stream is? A stream is something unpredictable. You get 1 byte to encrypt, or you get 5 bytes to encrypt, and you expect the encrypted data right away. So you just add more data, and you get ciphertext on the other side. Yeah, the example of the stream cipher would be Cha-Cha or Salsa, and Salsa 2.0. There's a family of streams. But the IES, the most popular, is a block cipher. How it works? The block cipher always encrypt 1 block at a time, right? In the case of IES, the block is set for 16 bytes, so you have to give the IES 16 bytes to get the 16 bytes on the output. But what if you have 4 bytes to encrypt? What do you do, right? But there is a solution. But it's more complicated. These block ciphers use block modes, so it works in some mode. Each cipher has defined list of the block modes you can use with that. I will just emphasize 2 here. One is counter mode, CTR, and the other one is CBC. It's a cipher blockchaining mode. The CBC is important because that is most likely the default you will get when you use a library. So let's see how they look. CTR, the first one, counter mode. If you look here, that each block is encrypted independently, right? That's advantage of this block mode. It means that you can encrypt or decrypt in parallel chunks of your messages. There's a counter. There's nonce. Nonce is some random value. And there's no dependency between previous block and the next block. Another property of CTR is that it makes the block cipher works as a stream cipher. Yeah, I know. Yeah, so it allows us to use IES as a stream cipher. It lets you encrypt 1 byte and get the result right away. But look at the CBC. CBC is the most popular. This is the default, probably. And in theory, it's safe, but it's very easy to use it just wrong. It works like this. So there's a plain text, there's a key, and there's a ciphertext. And this ciphertext is used to encrypt the next block of the message, and so on and so forth. So there's a chain. Right? It cannot be calculated independently. And this value, this IV here, initialization vector, you remember that there was one of the parameters. Initialization vector is just random value. It's a public value, random, but it is important to remember that especially when used with a CBC mode, IV has to be random, and this value can be used just once with the given key and given message. So you have to generate the IV value for each encryption. That would be the best. Usually it is just appended to the ciphertext, so it's part of the ciphertext. But look at the common crypto. This most popular function, it assumes here a CBC mode, and it lets you use the null value for IV. If you pass the null here, it will use all zeros. That basically breaks this whole thing. It's very unsecure. There are attacks that can be applied against that kind of encryption. So you think you use the library that is, FIPS 142 something certified, but it's really easy to be misused. Okay, the next parameter is padding. You may know what the padding is, you may not. Yeah, this is the issue. The issue was I was trying to encrypt Arabic numbers and it crashes. Yeah. Well, it doesn't matter. There was Arabic numbers, it crashes. It crashes because why? Because he used CBC mode, that is block mode. You have to put 16 bytes of data for the IES, and he chose to use no padding. If you choose no padding, your input is just 4 bytes or something. Let's say it's 4 bytes. It's not enough to encrypt. And padding will fill this remaining bytes. That's the kind of padding that we can use. PK, CS5, and 7 is the most popular. You should use that one. They are compatible, so either use 5 or 7. Let's better use 7. But 7 is backward compatible with 5. The other one is zero padding and no padding at all. PKCS7, good name, works like this. Let's say that our message is just text. So we have this remaining bytes, right? What do? Well, we put the number of the remaining bytes for each cell here. So when we decrypt, of the code. We just get the last value, and we know that we should discard 12 bytes, and the text will be output. A zero padding, use it only if you have to, only if you protocol define that, because how it works, it says, okay, use the zeros for the remaining bytes. Yeah, so that is fine, it works fine, as long as your last value is not zero, right? If it is zero, it will be discarded when decrypted, so you lost some data. And no padding. No padding is used with counter mode. So all the streams, if the block mode has a stream in the name, either is counter mode, OFP, or whatever, use no padding because the padding is not needed there. So having a padding, knowing how it works, don't remember the year, but there is an attack that lets you decrypt the plain text only based on the knowledge what is the padding. Well, basically, padding or oracle attack. You might find it with the name Poodle attack. Yeah, Poodle attack. I mentioned that because this attack is possible on a SSL protocol and TLS protocol up to version 1.2, and this is the current version we use. Well, it's the most widely used version, but the newest version is 1.3, and basically the version TLS 1.3 said you can't use CBC mode, so this attack is no longer relevant. How it works. All you need to make an attack is you need one block of ciphertext. This is a plain text, is unknown, and this is some data that you think will be the output, right? So what do we do? By modifying 1 byte of the previous block, we modify 1 byte of the following block. So yeah, here, just modify to whatever, first byte, second byte, and send it to the server or to the decryptor. It's called Oracle, and ask, it is successfully decrypted or no, or not. Yeah, he answer, yeah, it is success. Okay, try now. Oh, it's error. What does it mean? That means those are 6. This is the padding, right? Last 6 bytes is our padding. So what we know is that in that block we only have to decrypt 2 bytes because everything else is just a padding. Now, some math. We modify our ciphertext because we can. Modify the ciphertext we have and we know to change this padding to 7 because why not? And send that to the Oracle. And the Oracle will tell, okay, I was able to decrypt this ciphertext or not. If I was not, I was not. But I will change that value until it will succeed, right? It's a magic. When it succeeds, with some basic math, but it's really basic. I mean, it's not complicated. It just looks so. We can figure out that the plain text is, in this case, 47 hex here. And we do the same with the next byte. And look, we didn't use a key. The only information we got was a ciphertext that is a public, because it's ciphertext, and the padding. That's all. That's all you need to decrypt the plain text. And the internet used that. Like all the TLS implementations are vulnerable for this attack. There are mitigations, but yeah, this is why we need TLS 1.3. Oh, it doesn't play. Yeah, it should be like this. Okay, once we know how to decrypt, the another issue I face a lot is compatibility. The encryption is standardized, so it's not really, it shouldn't be a big deal to encrypt with the one library and decrypt with the other library. Yeah, on a basic level, yeah, that's the theory. But if you deal with the libraries, actually, they always do something implicit. Like here is PHP, right? And the PHP use something with the data, and like here, this framework actually return JSON. When you expect just a raw data, it will return a JSON. If you don't know that, well, you are not able to decrypt the message with the other library, right? That's obvious. And the same with the OpenSSL. OpenSSL on the API level is compatible, but on the command line level, it's not really. You should know how it works. So each of the parameters may affect the output, the format of the output. And here, like giving this -salt means it will add that string to the beginning, then some random bytes, and this is the cipher text. As you change the values here, it may produce some different output. For the primitives, you're interested only with this part. Basically the same with the CryptoJS. CryptoJS is a quite old library, but what it does, it tried to be compatible with the OpenSSL. OpenSSL is good, but it's not perfect, and historically had an issue. The issue was that when you use the password, it will apply the function that will calculate the key, and it used just his own function. I don't know, yeah, AVP bytes to key, right? It's no longer in use. Today we don't use that. We use the the derivation functions. So if you don't know that, using the CryptoJS library, well, you just use the wrong key, because you have to apply to your password the same function to encrypt the same message. The key derivation functions are the functions that do some magic with your password, because there's a difference. The password is not a key. It's very important. Password is something you choose. It can be your name or your pet's name. But the key is the actual cryptographic value that is secure. Basically, going into details, it distributes the bytes in a way that that is unpredictable. Yeah, it's magic, and it's slow as well. It should be slow, not very slow, but it should be fairly slow. So when you brute force, it will take more time than just guess your password. Right? Okay, and yeah, and now we know what to do with all these values. First, we choose the cipher, which is IES or not. Key, that is not your password. Block mode, that is, let's say, CBC. IV, initialization vector, that is random. It's very important, it's random. And you choose the padding PKCS7. And then there is a MAC. MAC is another cryptography primitives, message authentication code. It's like a hash something that can, yeah, the other name is tag. How it's used. This is the tag that authenticates your message or your ciphertext. It's like a signature, but it's not a signature, but it's like a signature. How do you use it? So let's say you have a ciphertext with the IV, and you calculate tag around all of this message. Then when you decrypt, you check if the tag match, if the tag you calculated match the tag you get, and compare if the ciphertext was modified or not on the way. Right? Yeah, that's how it works. And you'll be surprised that if you forgot this tag, you get into the trouble. iOS version 9.2 introduced the vulnerability for the iMessages. It was about 1 bit, as far as I remember. And they forgot to use that bit in a tag. And yeah, as a result, you could just decrypt iMessages, right? So it's not very good to not use that. And the last, the key exchange. Key exchange is a part of the asymmetric cryptography. Diffie-Hellman, so on and so forth. RSA, right? Why do we use asymmetric cryptography for? We use that only to transfer the symmetric key, because asymmetric cryptography is slow by definition. So it's too slow to encrypt the whole message, and it has other limitations. So what do? We just get the, we use the public key to encrypt the generated session key that is decrypted on the other side, and we establish, let's say, IES protocol, right? And since we exchange the keys, we just use the normal symmetric cryptography that is fast, and it just works. Yeah, it's here. Generate a session key that is the random, encrypt session with the public key, then decrypt session key with the private key, and establish AES encryption. That's how it works. And I don't have a closure because yesterday was a party and I didn't have a time. So yeah, but the next slide is thank you. So yeah, that will be all. Thank you. I know the topic is a bit maybe hard for the last talk, but yeah, if you have any questions. Oh, Jesus. There is actually a question. Yeah, I didn't see that coming.
I mean, thanks for the speech. I understand the difficulties to this kind of questions, but it's something that really impressed me a lot when I'm programming some apps, especially with iOS. When I have to put my app into the store, I always find the problems, especially in these days, to really understand what are the kind of questions that the store is asking me about encryption and decryption in my app, and what I should actually answer to this kind of question to. And where to look into my code to understand, I mean, what is the problem or what is the right question to answer when the store asks me to how I use the encryption inside my apps.
It's a good question. Although the answer is vague. I don't know the good answer because the questions in the App Store are based on the local regulations in the countries. So they ask because they have to. Like there's other regulation in France, as far as I remember. There's something for the US. It's connected with the export of the encryption. The European Union. I don't know the good answer. They say something like, if you use our framework, you probably shouldn't. You don't have to fill all the papers. But some say you still have to fill the yearly report. There is a on Medium. There is a blog post that is trying to be up to date about the current state. I know there was some changes just recently in the guidelines, but I really can't. There's no like a simple answer to that.
Thanks anyway. Is that just that feels every time like a guess? I mean, when you have to compile that kind of answer in the store, so.
Yeah, it's very annoying because from the one on the one side, Apple force you to use like OpenSSL, right? Not OpenSSL, sorry, SSL. Force you to use SSL, and you use SSL for communicating with your API. On the other hand, they put that papers on your back, and you don't really know what to do. And you can fake. You can just say no. You're all fine. They will probably not check that.
Thanks.
Yeah, there's one more question. That'll be all.
Hello.
Hello.
How's it going? Good?
Yeah, good.
Good. So I think I understood 20% of the talk, like more or less. Now, I got a question. I was interested when you were talking about these modes, like the CBS or the other one, which, yeah, it's encrypting block by block, right? So that means that you can run them in parallel. But you said the CBS is the most widely used, right?
Mm-hmm.
And I'm interested in the other one. Like, so with CBS, you cannot do it in parallel, right? You cannot encrypt it because it's using one block to encrypt the next one, right?
Yes.
Yeah.
Yeah, that's the one. Yeah, you can. You can. What is changing here is just a counter. There's nonce that's based on the IV value you get to the cipher, and the counter is something you control. So I can imagine you just reserve values from 1 to 100 for the one batch, and encrypt on one thread, and get the another batch for the another thread. At the end, well, you know the counter. You just have to combine the ciphertext.
Okay, but with the other one, you cannot do it in parallel,
No,
right? Because,
no,
you're using as an entry point the other one, the other block, right?
Yeah. Yeah.
Okay.
Yeah.
Cool. Okay. Thanks for the explanation.
Thank you very much. Yeah, that will be all.
Oh, steady on.
Oh yeah, no, there's one more question. Sorry.
I'd like to anyway.
Oh, please. Be my guest.
So I was with you up to when you said, hello, my name's Marcin.
Oh yeah. So it was like about the gold, right?
Pretty much. So obviously adding security to an app is a good thing, makes your app more secure. But when people who don't get security, like me, quite frankly, do it, we often do it badly, and that's sometimes worse. We think we're secure, but we're really not. So what's your advice for people like me?
Don't use the primitives by yourself. Use the protocols, or use the predefined libraries that are on the market. Like one of it is encryptor, you may be familiar with, by Rob Napier. It's a good one, although it was the first version was vulnerable, but the current version is secure solid. So yeah, use the protocols. Do not try to build your own construction for the encryption. It doesn't make really sense. Yeah. Okay. Thank you. That was all.